Hello everyone, and welcome to our 72nd webinar on the Latin American webinars in physics. My name is Federico van der Palen from the Universidad Antioquia in Colombia, and I will be your host today. Our speaker is Natalia Tapia from the Universidad de Santiago de Chile, and she will speak about measuring the boiling point of the QED vacuum. So Natalia is currently a graduate student, a PhD graduate student at the Universidad de Chile, Santiago, Chile, but she's currently visiting the University of Montreal, and she spent 1 year visiting as an internship at DESY. And Natalia will speak about a very interesting subject, because we usually hear about the QCD vacuum, and she will speak about the QED vacuum and the work she's been doing with the colleagues at DESY. Let me remind you that you can be part of the discussion, writing questions and comments via our YouTube live chat system. And I will hand you over now to Natalia. So, Natalia, you can have now the board. You have to unmute yourself.
Okay. Can you listen to me?
Yes, great.
Okay. Can you see my presentation now?
Yes, perfect.
Okay, well, thank you very much again. I'm Natalia here. Thank you for letting me share my work with you. Today, I will show you the results of my last paper in collaboration with Anthony Harting and Andreas Greenwald at DC, where I spent 10 months doing an internship. The project involved strong field QED and the measure of electron-positron perturbation in this new experiment at DC, the LAXI experiment, very similar to the SLAC experiment performed in the 90s. We are all aware, or we all know, of the successful of the QED theory, but there are some observables of the theory that are not possible to achieve by means of perturbation theory, as the rates of spontaneous perproduction. But there are some related processes that you can measure in nonlinear experiments. So before I'll show you my results, I would like to talk a little bit of the history or the context of this kind of experiments. So, can you hear me?
Yes, don't worry, we can hear you.
Yes. Okay. So, can you see that I changed the slide?
Yes, that's perfect.
Okay. So, the first attempt to measure a nonlinear process was performed at the SLAC experiment in the 90s. So, this collaboration focused on an extremely intense laser beam at a beam of high energy electrons. This picture that you can see here appeared in the November 1997 issue of Photonic Spectra. And you can find all these pictures, documents, news about the experiment, paper, PhD thesis related to the experiment in the SLAC repository. And in this experiment, it was the first time in history where perproduction or light-by-light scattering was measured from real photons. So basically, in this experiment, they collided a high-energy electron beam with a laser, which at the focusing point had an intensity of around 0.5 times 10 to the 18 watt per centimeter square. So this number you can think is very high, but actually is below the non-perturbative regime, where you can somehow measure the critical field. So when the laser photons collided head-on with the electrons from the electron beam, they got a huge energy boost, much like when you throw a ping pong ball through a track in movement. So the ping pong will get a lot of momentum from the track and will go away with a higher acceleration than it was in the beginning. So these high energy photons that are produced when the electrons collide with the laser photons, then can re-interact with the laser incoming photons and producing electron-positron pairs. These pairs are sometimes produced in accelerator experiments at high energies, but the photons involved in the process, at least one of them was a virtual photon. So this experiment marks the first time in history that real photons interacted to produce visible matter, electron-positron pairs. So this old animation shows what is the experiment about. You have the electron beam in blue colliding with the laser, and in the same path of the laser, this high energy photon in green produced from the previous collision will produce an electron-positron pair. So before in around the 85, Kirk McDonald, one of the spokesperson of the SLAC experiment, established 3 different nonlinear processes that could be measured at this experiment. So by the time, the greatest acceleration that they could obtain in a laboratory was the one of an electron in a high-intensity laser beam. They were expecting to measure different nonlinear processes with these highly accelerated electrons. So they considered the case of a very unusual, strong electromagnetic field. So what are the kind of processes that they were expecting to measure? For example, that always called the attention is Hawking radiation and Unruh radiation. In the case of Hawking radiation, you have an observer at rest near to a black hole. And due to the high acceleration produced for the very strong gravitational field around the black hole, this observer will be involved in a thermal bath, and it will scatter this thermal bath by means of emission of high energy photons. A very similar process is the Unruh radiation, in where a highly accelerated particle, in this case an electron, will also feel a thermal bath around it, and it will scatter the thermal bath by emitting high energy photons. So these high energy photons could be measured by some observer in the laboratory. But this is still an experimental problem, and how to measure this kind of radiation, and it has still not been solved, but it's always present in the propositions for this kind of experiments. So you could also measure various possible effects of vacuum polarization as light-by-light scattering, or multiphoton effects as spontaneous perproduction, stimulated perproduction, and you can also expect to see limits in the energy of the field due to the cascade process, in which you will use the energy of the laser in the focusing point, due to at some reference frame, the particles will have enough energy to produce electron-positron pairs spontaneously. So that will be a limit to actually reach the critical field for QED. And by the time, the most accessible process was higher harmonic radiation of Thomson scattering. So just to see some numbers, for example, for light-by-light scattering, we know that this is a 4th order in perturbation theory, the interaction of 2 photon particles. and it happens by means of the virtual production of electron-positron pairs that then annihilate into two photons again. A related process is photon-photon scattering, giving rise to electron-positron pairs. So in this case, the cross-section goes as the fine structure constant to the fourth power, and it will also depend on the energy of the photons involved in the process. So if you use the appropriate units in MeV, you will need 10 to the 15 photons of 1 MeV to be brought into collision to observe one pair. So usually the laboratory beams around the MeV range have typically less than 10 to the 10 photons. That is why it's not possible to see this kind of process. So what they propose to observe nonlinear processes is the study of the scattering of 50 or around 50 GeV electrons and a laser with peak energy flux of 4 times 10 to the 18 watt per centimeter square. So there are two considerations in how to measure how strong is a field. One of it is when the electric field in the process is higher than the critical field, and this is quite difficult to achieve. The other way to measure that the field is strong is when this quantity is bigger than 1. When this quantity is bigger than 1, is considered the static limit, or the frequency is much smaller than all these other parameters. This parameter psi is also called the nonlinearity parameter or the laser parameter, and it's strongly related with the nonperturbative limit. When this parameter is higher than 1, the fields are considered to be strong, the process is considered to be nonperturbative, and usually it's also nonlinear. Due to the effect of the electron traveling in an electromagnetic wave, the mass of the electron will suffer some changes, or seen from the outside, you will see an effective mass. The electron will move in a transverse way to the laser, so it will add momentum to the particle, and the electron will be heavier when you increase the intensity of the laser, for example. The parameter psi is also related to the intensity of the laser. So if you increase the intensities to see a higher nonlinearity process, the mass of the electron is going to be heavier. And that will be translated later in a higher number of photons involved in the process to see one pair production. So finally, what they observed in this experiment was nonlinear Compton nonlinear Compton scattering and electron-positron pair production for electrons around 50 GeV. And the laser intensities peak were around of 0.5 times 10 to the 18th watt per centimeter square, which corresponds to a laser parameter of around 0.4. As I said before, you need to be up 1 to see non-perturbative process. So all these measures that they get were not in the non-perturbative regime. However, these were the first laboratory evidence of inelastic light-by-light scattering involving only real photons. In the case of nonlinear Compton scattering, they observed absorption of up to 4 photons. That means that they observed nonlinear scattering for 1 to 3 and 4 photons in one process. The setup of the SLAG experiment was something like this. They had the electron beam here of around 50 GeV colliding with the laser, and in the same spot of the laser, they will reinteract the high energy photons produced for nonlinear Compton scattering, for example, and then the electron-positron pair production. And the particles that don't interact here will be collected further. In our case, we propose something a little different. We propose first to obtain high energy photons by means of Bremsstrahlung. So the beam of high energy electrons is going to be around 17.5 GeV, at the LUXI experimental TC will heat a Bremsstrahlung converter foil, a thin foil, and they will produce high energy photons here. So once they have the high energy photons, they will collide them here with the laser at the focusing point, and here with these high energy photons and a number n of laser optical photons, there will be pair production. So for the LUX experiment, it's expected the laser to be a 1 petawatt laser system of around 35 femtosecond bunch, and with a focal area of 10 micrometers squared, and with a peak intensity of around 10 to the 20 watt per centimeter squared. The electron beam is going to be of a size of 50 micrometers and with a repetition rate of 10 hertz. So as I said before, we consider this as one photon per production, but this process is in the background of the laser. So this high energy photon here has to interact with an n number of laser photons to produce these electron-positron pairs. These particles are also called dress states because due to the laser or to be in the background of the laser, they will have different states. These are called Volkova states. And when you use them, you are already considered the nonlinear effects. So we are considering a Bremsstrahlung spectrum to the pair production in the background of the laser. And these are the dress states that I named before. So the one photon per production that we are considering is going to be a nonlinear process. And if we compare our rates later that we will obtain with the spontaneous pair production rate that you obtain from the Euler-Heisenberg-Lagrangian, you obtain that the vacuum will decay in electron-positron pair production in this way. The dependency in the exponential here with the critical field also hides the dependency on the electric charge, that is the coupling constant of the theory. So as you can see here, if the coupling constant goes to 0, the exponential diverges. And that means that you cannot obtain this result by means of perturbation theory. That is why it's considered to be non-perturbative. So here you can see in the exponential the dependency on the critical field that is around this value is expected to be 1.3 times 10 to the 18 volt per meter, and the dependency on the coupling constant. So the Volkova states or dress states look like this. And from here you can see where this laser nonlinearity factor comes from. This will affect the mass of the electron, and you will have an effective mass that depends on the laser nonlinearity parameter. So if you increase the intensity, the electron is going to be heavier, and that will mean that it will need more and more photons to produce one pair. So other important parameters in these experiments, as I said before, the laser parameter are the photon and electron recoil parameter. This depends mainly on the kinematics of the process, on the energies of the photons involved, the mass of the electron, and the angle of collision. So this is the rate for electron-positron pair production when you consider the Volkova states. So you can see here that it goes like some powers of Bessel functions that depends on the zeta function. So you can see here that the argument of the Bessel functions depends also on the laser nonlinearity parameter and the photon recoil parameter. So the threshold number of photons here needed to produce one pair is here, and you can see that also increase with the laser nonlinearity parameter. So you will have higher orders and higher arguments for high intensity parameter. In this case, you can approximate in this range of parameters for psi much bigger than 1, and for photon recoil parameter less than 1, to this asymptotic expression simplified from here when the argument and the order is high by the device asymptotic expression. So here we can see that the asymptotic rate goes as the exponential that also depends on the electric charge and the critical field here or here. So you can see here that the electron positron perturbation rate from one photon, it also goes as the spontaneous perturbation in some extent. So these are the rates that we obtain with this with the function f that I showed you before here. So the full rates are the solid line here. The dot line is what you expect to be for a small laser parameter. This is the perturbative behavior. It means that it goes like psi squared for a process of 3 vertices. And for a high psi, for psi actually bigger than 1, you can see here the asymptotic result that actually fits very good for the case of psi bigger than 1 and for photon recoil parameter much less than 1. The other plots for different parameters are to compare the fit of the asymptotic result with the full rate. So you can see that indeed the best behavior is for the case for psi bigger than 1 and photon recoil parameter less than 1. So as we consider a Bremsstrahlung spectrum, you can find, for example, in the review of particle physics, the rate for a Bremsstrahlung spectrum, and it goes like this. So we use this rate to integrate our rate of perturbation, and we integrate in terms of the photon recoil parameter between 0 and the electron recoil parameter. What we get for the asymptotic result is this analytical expression. In the case of the full rate, we obtain a numerical result that I will show you. So if we look to the Bremsstrahlung perturbation rate in terms of the critical field, you can see again the behavior very similar to the asymptotic result obtained for the perturbation before the integration and in the spontaneous perturbation rate. So here we recover the non-perturbative behavior. So that will mean that even after this Bremsstrahlung spectrum, you will have non-perturbative behavior. And this would be a way to measure the critical field in this experiment. So here I show you again in solid line the full rate integrated, and the dashed line is the asymptotic result integrated in the background of Rameshwaram spectrum. So for different parameters, here we see again that the base behavior is for a small recoil parameter and for laser parameter bigger than 1. You can see that the good behavior starts from psi equal 1. And you can see here the rates produced of electron positron perturbation. And you can see that these are very high numbers, but actually the range of parameters for the large experiment is around here, the corner, the right corner. So for the peak intensities, the rates are going to be around 10 to the 4 per produce. So in the case of the experiment, it's much easier to vary the intensity and the energy of the electrons. For example, if you want to keep the photon recoil parameter or the electron recoil parameter and vary the laser intensity or the laser parameter, it is much difficult because the recoil parameters depend on the laser parameters. So actually you will have to move the laser to change the angle, for example, and that is much difficult. So it's much easier to vary the intensity and the energy in this case. Here we can see that the laser nonlinearity parameter around 1, that is where you can see the non-perturbative behavior and the nonlinearities, is going to be for an intensity around 10 to the 18. This is one of the reasons, even in the SLAC experiment, the energy of the electron beam was higher, why they couldn't get a non-perturbative behavior, because they were far less below this intensity. So here we see, in terms of the intensity, the rates of perturbation. For the peak intensity, here we see that the rate production is going to be around 10 to the 4, as I said before. Here, the solid line is the complete rate integrated, and the dashed line is the asymptotic result. So around 1 times 10 to the 18 watt per centimeter square, as I said before, is the laser parameter around 1. And the first pair is going to be produced around 2 times 10 to the 18 watt per centimeter square. That means that your first pair is going to be in the non-perturbative regime and is for a quite modest intensity. The dotted line in blue here is for the case that the nominal value of the critical field is smaller. We wanted to get something like an error bar here. So if you have a 10% lower value of the nominal value expected for the critical field, you will have higher rates, and this makes sense because if this kind of potential barrier to get perturbation is smaller, you will have more rates. And if the value of the critical field is bigger, you will have less rates because it's more difficult to produce the pairs. So in this case, for the experiment, the energy of the electron beam is going to be 17.5 GeV with a bunch of 6 times 10 to the 9 electrons per bunch, with a Bremsstrahlung foil thin in comparison with the radiation length of the material used, and with a laser shot of 50 femtoseconds, an angle of P12, and the energy of the laser photons of 1.053 electron volts. In the case of the variation of the energy, the rates are going to be for an energy of around 14 GeV, you will see a first pair, for an intensity fix of 3 times 10 to the 19 watt per centimeter square. We know already that for this parameter, the behavior is non-perturbative. So you will have your first pair around 14 GeV, and you will see around 20 pairs for 17 GeV, 17.5 GeV for this fixed intensity. So in conclusion, we can see that the behavior of the electron-positron perturbation will behave very similar to the spontaneous perturbation rates. Here we can see the similar behavior on the exponential dependency on the critical field that hides also the dependency on the electric charge, that is the coupling constant of the theory. So even in this very restricted range of parameters that you need to get the asymptotic result, where you have the non-perturbative limit, you will have the number of pairs high enough to see something in this kind of experiment. And it will be possible to measure the Schwinger critical field for these modest intensities. Around 2 times 10 to the 19 watt per centimeter square, you should be able to see one pair in the non-perturbative regime, and with a 10% discrepancy with the nominal value of the electric critical field, is expected to see a high rate of electron-positron perturbation, and this varies around 1 order of magnitude for small intensities, and for higher intensities, this effect becomes less important. So, well, these are my reference. Thank you very much for your attention.
Thank you, Natalia, for this very clear talk about the subject, which is new to me, but I think I learned something. Now, let's pass. Let's see if there are questions from the board or from YouTube. Roberto?
Yeah, I have a couple of questions for Natalia. First of all, Natalia, thank you very much. It was very interesting, in fact, your talk. So I have one question that is more kind of a little bit naive, but in the sense that is it possible to observe this kind of process, the one that you were talking about, this boiling point in QED vacuum, but in some astrophysical environments? I don't know, in pulsars physics, because also you have very intense electromagnetic fields that could also bring electrons and all the stuff.
Well, the Hawking radiation is related with this process, in when you can have actually a very intense electromagnetic field in astrophysical environment. So near a black hole, you will have, for example, a pair production, and you will have a virtual pair. So it's thought that due to the very high gravitational field, one of the particles can fall inside the event horizon, and you will have at least one real particle produced near to the black hole. So this particle can escape, and you will have one particle produced, and this particle will need some energy from somewhere, right? Mm-hmm. So the energy comes from the black hole. So this is translated as the Hawking radiation, this loss of energy due to the pair production. So in this kind of process, you can see pair production. That is one way to think about it.
Yeah, but in the sense of, if it's, I understand with the Hawking radiation, but do you think that it's possible to observe the effect I mean, I know that Hawking radiation is super hard to observe nowadays with the technology that we have at the moment, but I don't know, in other type of, I don't know, gamma ray burst, that also there are very strong photons emitted, and I don't know. No, it's just a question is kind of.
Yeah, no, I understand, but I don't know if we are able to measure something like this. This process should happen in the universe, right?
Yeah.
At some point of the history. But how we measure this is, I really haven't think about it. It's actually difficult now to measure Hawking radiation in a laboratory or Unruh radiation. So I hope maybe in the near future, or not so near, it will be possible.
I guess so. So.
Okay. I have a naive question.
Okay.
Then we can have another question. And I was thinking, what do we learn with this experiment? I mean, do you expect to confirm QED, or could you eventually find something new, or new techniques in non-perturbative regimes of QED, or even other models?
Okay, so first, when I started my talk, I always like to talk a bit of the SLAC experiment at the Stanford accelerator, because I always think what they wanted to measure by that time. In that time, they wanted to measure nonlinear QED, and they measured it. Now the idea is to see the non-perturbative regime and indirectly measure the critical field. And if it's what it is expected, it will be a way to test QED and in a very extreme condition to test the theory. But there can be the case that you can find something different. So that means that you have to reformulate the theory and keep working.
Right. So my question is, when do we know that we are within the range of errors, or that we have to change the theory? I mean, my question leads to the following. QED is quite well established, but when you go into the non-perturbative regime, maybe you have, beyond the standard model physics appearing or not. I don't know. Do we have any possibility to measure something that goes beyond the standard model, and what could it be?
Right. I mean, the theory says that we should measure something with this behavior that I show you. And that would mean that, okay, the behavior is non-perturbative as it is expected by this result by Schwinger, right? But if it's different, I think we are like, okay, what do we do now? Because there are not other ideas about it. We are expecting to prove the theory to be like this, right? So if we find something different, it would be also nice, right? Because then we find something funny maybe, or something that we are not expecting.
Okay, thanks. No, I mean, because in some theories you expect something new, like flavor physics,
Yeah.
and in other cases, like neutrinos traveling faster than light, you don't expect that. I mean, that's a result where you say that's probably wrong, the experiment, because it's so out of the way. So in this case, is it possible to find something different, or would it be something like, neutrinos faster than light, which are clearly totally wrong?
I think that when they perform the experiment, they will measure this. There's no I think that there's not like a big chance of measure something different actually, because QED we know is well tested and it has worked until now. But it can happen that in some extreme range it doesn't work. But there are no other ideas that I know, at least, how QED will behave in these extreme conditions.
Okay, thanks, Roberto.
Yeah, and in fact, there is also a question in YouTube, but then first I'm gonna do my question, and I'm gonna ask my question. Yeah,
Then
the
I'll
other
ask
question
you.
that was, in fact, is kind of related with the stuff that Federico was saying, that because in principle, we in the context of the standard model, we know that the QED at some point start to get mixed with weak forces. So to have the electroweak processes that are very well known, let's say, that also is well tested. So do you expect also to more or less in which range you start to have this correction due to the Z and W bosons, or production maybe of neutrino that would appear like kind of missing energy for your experiment, or I don't know, kind of, because if you start to test QED in the non-linear regime, that means that in some sense, your energy that in your processes start to be very high. So maybe in that sense, also you could start to perturbate the weak modes of the because at the end electrons are also has a isospin. So I don't know if you can understand what because I'm trying to
Yeah, I
figure out
understand, but I actually I don't have any reference of how possible would be to see something. I mean, in this kind of process, you could see spontaneous perproduction, as I said before. This is a laser-assisted perproduction because we produce the photons before. So you will have a spontaneous reproduction, but all nonlinear QED process actually. At this point, I think it's only QED.
it's only QED. Ah, okay.
Yeah.
That's good. Yeah, because in fact, the kind of the stuff that was saying Federico, in the sense that if you start to see a deviation with respect with QED, maybe it's not faster than light neutrino, but it's only maybe could be weak processes that start to perturbate your model. But yeah, but in this sense, yeah, makes sense.
Okay,
Yeah.
so now we have a question from Bhavesh Chauhan. I hope I pronounce his name correctly. So is it possible to also produce muon pairs? So what would be the expected rates?
Okay, so first to see muon pair production, you will need to have a muon accelerator to have the very high energy muons instead of an electron accelerator, right?
But he was probably asking about the pair production, which happens after the laser produced spontaneously.
The process after you have the electron positron pair production.
That's what I understand that his question is. Otherwise, he can reformulate it.
Yes, because actually, if you have an electron initially and photons, you will, I mean, unless lepton number violation is considered, you will have electrons, right?
I think you could produce muon pairs, but the problem is they have a mass of around 200 times larger than
Yeah.
the electron, so you probably don't get to the energy.
Yeah, that's one point also. But first, you will need a muon beam to collate with the laser, and then you maybe will see muon pair production, but you will need much higher intensities to go above the energy that you need to produce one pair of muons, right?
I don't know if Bhavesh has something to say. I think that you don't need a muon beam. I mean, but okay, I don't know about the subject, but I think that once you have the photon, the very energetic photon, which, by the way, what's the energy of those photons in the few GeV, I expect?
Yeah, it's expected to be around the 5 and 15 GeV.
Yeah, so once this photon, this is a virtual photon or a real photon,
Yeah.
but which spontaneously uh, interacts with its own field and so produces a pair of decays basically in an electron-positron pair.
Okay.
So it could also decay into a pair of muon anti-muons.
Yeah, I think there has to be some probability that this process happen, but probably at higher intensities.
Yeah, probably the rate, which was his question, is very small, but on the other case, this would be very nice events because it would be very clean.
Yeah, probably around the peak intensities in the case of Laxi experiment, yeah, you will have maybe one in, I don't know, a very high numbers of electron per production.
Okay, let me see what he's saying. Do we really need a muon beam? No. I mean, E was around 17 GeV, the energy of the electron. I do not see why muons cannot be produced. I think this is what we discussed. So,
yeah. I mean, there has to be some. But what I'm trying to say is that I think if you are only consider the electron beam to produce muon pairs later, the rates are going to be quite small. I don't think of this experiment as a way to produce per production. I see that the other case would be maybe the right way to see. If you really want to see muon per production, you have to do it in another way.
all right. So, okay, but in any case, I think it could be a simple exercise to change the mass. Instead of putting the mass of the electron, put the mass of the muon and see the rate. And who knows? I mean, sometimes naive questions are, or not so naive, I don't know, but are lead to something. So I have also another naive question. And basically, a few years ago, they were discussing as an option for the linear collider. A few years, that's beginning of this decade.
Okay.
A gamma-gamma collider option. But then they dropped that option, but some people continue to say we want to use these free electron lasers colliding with each other and producing gamma-gamma collisions. So these collisions come also in this regime? I mean, colliding gamma-gammas, basically. So having two lasers hitting at each other. So would you go into this regime or maybe at a higher energy regime?
Okay, I've heard of this kind of experiment that is going to be performed in Shanghai. So there is people thinking about measuring this kind of laser interactions. But in this case, I'm not sure about the numbers because you will need very high energy for the laser to see some pair production. As I showed you before, we first produce the high energy photon in a previous process in order to get higher energies.
Yeah. I mean, the point is that now when two lasers collide, you are in an experiment where you can focus on the center of mass system, and so the energy. I mean, whereas in your case is an experiment where you hit a target, so the center of mass energy is not so high as the energy of the photons, right? Because you have a moving center of mass. So in this case, you can achieve a higher center of mass energy. And I don't know what the status is. I mean, 5 years ago, people were still very exciting. And then they decided to build a linear collider without the photon collider option, and then they stopped the linear collider option altogether somehow. Okay.
Yeah, I think it's an interesting case also. I haven't really checked the numbers of the rates, but it's also very interesting. And yeah, probably you will see at some point some process, but I really am not sure of the numbers. So I will be lying.
All right. And another naive question, and basically, I mean, light by light scattering is very important, for instance, for radiative correction, for G mu minus 2 corrections, for instance, where you have large uncertainties. But there, the uncertainties are QCD and not QED. Does this relate to the Lux experiment or not?
I would say no, this is only QED processes.
All right.
So
Okay.
this is probing QED in extreme conditions.
Thank you. Okay. So I mean, I asked more than what I was expecting from a subject where I learned something, but I didn't know anything. So I don't know. We don't have any more questions on YouTube.
I have one more question. Nobody kind of also all the time thinking beyond standard model cases. So do you know, or maybe other people also try to do this? Because there are all these theories that propose that there is dark photons that are kind of similar to the photons, but just not as visible as the one that we know. Yeah. So, or maybe other type of particle like ALPS, like action-like particles, even though they are not the action from QCD, but you can have some kind of action that couples to leptons. So is it possible, I'm not saying that in your theory to include this, but in the sense, is it possible to use the same experimental setup that you were explaining to detect this type of new particles, or kind of the experimental setup that you explained is only for testing QED processes to this non-perturbative regime or something like that?
Okay, there were some ideas. Sorry, there was okay. There are some ideas. Instead, of using a thin foil, to use a thicker foil, and to have a laser before, so you will have something like light shining through the wall in the first process, and then making this interact again with an electromagnetic field to measure something. There are some ideas for this experiment. Later, they prove the QED processes. Yes, there are some. I know that there are some thoughts about measuring action-like particles with this.
Okay.
So yes.
Ah, good, nice.
Yes. And yeah, maybe later this will go to something like hidden photons or something like that.
Yeah. Ah, cool.
Yes.
Okay, thank you. So if there are no more questions, we finish this very great talk, and we'll meet in our next webinar.
Okay, bye.